Good morning, everybody, and welcome back to Next Door NetAdmin. So, like I said in the freeform from March, I have had a suggestion, a request to go over Acme certificates and the whole 9 yards. I could do that, and I'm planning on doing that. But what's the point of talking at length about Acme certificates if nobody knows what they are? So, I'm actually going to end up doing a three-parter here. This week, I'm going to talk about what I would call PKI basics. We'll get into what PKI is in just a second. We're going to go over the basics. What is a certificate? How do these actually work to a computer? And why is this all important? Okay, second week, we're going to go over the Acme protocol itself. What is it? How does it function? How is this actually planned out so that it's secure and it's doing what it should do? Cool. And then in the third week, we're going to go over implementation. What are some tools that we can use to manage Acme certificates? There's more than just the one. How can you actually make this a functional part of your IT infrastructure? For those of you who are not sysadmins or netadmins yourself, I'm going to be trying to keep this relatively basic and understandable. I realize implementation may not be your thing, but there's going to be plenty in the other weeks that will help you increase your understanding of what these certificate things are, why they're important, and kind of a general understanding of how it works and the kind of considerations that go into designing something that is both usable and relatively secure for most purposes. Okay, so with that in mind, let's get started with this week's lesson. That almost sounds so formal. I'm just going to start talking, okay? Awesome. PKI basics. PKI in this case is public key infrastructure. It's important to know that everything to do with certificates uses public-private keys. What is that? Well, the general idea is it's a way of handling encryption where there are two keys involved. There's a public key, which is public. It's open to everybody. Everybody gets to see it. Everybody knows what it is. And then there's a private key, which is kept secret. There's a lot of complicated math that goes into this. I'm not going to get into all of the complicated math, don't worry. But I am going to give you a broad overview of how it works. Right off the top, I'm going to come clean. I'm using the numbers off of the Wikipedia entry, okay? Because they're simple numbers, they're relatively small, and they're more easily understandable. The actual numbers involved are many, many, many times larger. But we're going to keep things simple. I'm going to walk you through the basic idea of the math behind these two keys, and then I'll come back and I'll tell you why this is kind of important.
So we have a bunch of numbers here. This looks intimidating as all get out, I realize. Stick with me though, we're going to make this as basic as we can. First thing we need to understand is modular arithmetic, or the modulo operation. We all know how to add, subtract, multiply, divide. This is stuff that's very basic. But what are we doing when we look at 8 mod 3? Well, the easy way to think of mod is as remainders. So when you see 8 mod 3, if you take 8 divided by 3, what's your remainder? Now, mentally in our heads, we can all do this. If you divide 8 by 3, well, you can divide 6 by 3 easily, and 8 minus 6 is 2. Okay, so the remainder is 2. mathematically speaking, if you pull out a calculator or open up the calculator app on your PC, and I do encourage this for following through with this, if you do 8 divided by 3, you'll get a number like 2.umpteen zillion sixes followed by a 7. If you subtract just the integer part, the part before the decimal point, you hit -2, then you'll get that, and then you hit times 3, the number that you were modding by, and you'll get 2. This is really useful. This is going to be the keystone of what we're doing here. So when we are constructing a public and private key pair, you start by getting 2 different prime numbers. We call them P and Q. These are very small prime numbers. You wouldn't actually use these because they're not secure enough. We're using this as an example because it's easier to work with numbers of this size. The prime numbers we actually use in public-private key cryptography are 300 plus digits long. They're ungodly length for us, for humans. For computers, whatever. But the length of the prime number is what actually makes this secure, because it makes it very infeasible to reverse what we're actually going to be doing with this. But for our example, we're just using 2 small numbers, again, like I said, lifted liberally from Wikipedia. So I'm just walking you through this example. We have 2 prime numbers, 61 and 53 here, P and Q. And then we're going to calculate the product of P and Q, which is N. If you punch this into your calculator, you will find that it comes out to 3,233. Now, again, I am glossing over the math. We also want to find the least common multiple of P minus 1 and Q minus 1. So the least common multiple of 60 and 52. It's not the same thing as multiplying them together. In this case, the least common multiple turns out to be 780. Take my word for this. But this is also referred to in the math as lambda, the Greek letter lambda. Probably familiar to you from the Half-Life franchise. Then you need to choose a number which is greater than 1, less than 780, and has to be co-prime to 780. Now, for many reasons, it is optimal to choose a small-ish prime number, but you could choose any number. It's just best to use a smallish prime number because for making sure that it's co-prime, you just have to make sure that whatever you choose is not a factor of 780. You cannot evenly divide 780 by 17. That's fine. So our number here is going to be 17. That's the one that we chose. Then we need to choose another integer, d, and it needs to satisfy this equation. E times d mod lambda equals 1. There's an actual mathematical calculation you can make to correctly get this number, but again, we're skimming over the heavy stuff. It's enough to know that 413 in this case satisfies this equation. So if you punch into your calculator 17 times 413, divide it by 780, subtract whatever your integer is, and then multiply it by 780, you should get exactly 1. This now forms our actual keys. The public key is the pair of E, 17, and N, 3,233, and the private key is the corresponding D and N, so 413 and 3,233. Okay, that's a bunch of numbers. How does that actually help us whatsoever? Well, stick with me. We're going to use some more complicated maths, but stay in your calculator, just punch it through, and you can confirm that this works. You may need to switch your calculator to scientific mode. If you're using the Windows Calculator app, for example, you can choose scientific. That will help you in what we're about to do, okay? Okay. So, just as a reminder, here's our public key, here's our private key, and I've actually put in the numbers here so that we can do this. Now, we have a message. Remember that to a computer, everything, including text, is a number, or can be represented as a number. So the letter A, the capital letter A, is represented in ASCII code as the number 65. So our letter is A. In this case, it's the number 65. That's our message, M. C is our ciphertext, the encrypted version of this. To calculate C, you take M raised to the power of E, 17, mod N. So it'll look like this, equals 65 to the power of 17, mod 3,233. If you punch that through in your calculator, again, these are numbers big enough that you're not going to calculate them in your head unless you are genius, and I am not. When you punch it all through, you should get 2,790. Okay, cool. To decrypt it, you have pretty much the same equation, but using the ciphertext instead of the message and using your decryption value rather than your encryption value. So if your ciphertext is 2,790, your message is C to the power of D mod N. And it looks like this, 2,790 to the power of 413, yikes, mod 3,233, and what you should get is 65. We've used one of these to encrypt the message into ciphertext, and the corresponding one has decrypted it back into the message. Now, here is a very important property. If you do this in reverse, it still works. Your ciphertext can be your message to the power of the decryption value, 65 to the power of 413, mod 3,233, and that'll equal something completely different. But when you use the corresponding half, the encryption value, you can retrieve the original message. So these equations work both ways, and that's a very important factor, as you'll see in just a moment.
Now, the math that I've just walked through here is valid for what's called RSA keys. RSA is just the initials of the people who developed it. It doesn't stand for anything more complicated than that. Regardless, these are the older style of keys used in public-private key cryptography. They're still valid. They're still secure. They're still used. They're still actually required for some very specific purposes. There are newer keys as well using something called elliptic curve cryptography. This is also shortened to ECC. ECC keys have the definite advantage of being much smaller for the same degree of security. An RSA key that is 2,048 bits long, you can get equivalent security from an ECC key that's only 256 bits long, 8 times smaller. This has major benefits when you're working with mobile devices like phones or tablets. It consumes less power. It transmits faster because it's 8 times smaller. It's hugely beneficial and recommended to use ECC keys these days wherever you can. Cool. I'm not going to walk you through all of that because all you really need to know is that the same fundamental principle applies. And this is the key point, pun intended. Anything that one half of the key pair does, public or private, the other half can undo public or private. Public matches with private, private matches with public. Cool. Why is this important? This property is what underpins all of the certificates in the world. Because when you use the public key to encrypt something, only the receiver's private key can decrypt it. This is basic. But if you go the other direction, anything that the private key encrypts can only be decrypted by the public key. And this forms a signature. More specifically, if you take an entire document, or let's say public key itself, if you take that data and squash it down and create what's called a hash of it, a hash very basically is a representation of the input. You can't get the input back from the hash, but the idea is that if you change anything in the input, you'll get a different hash value. So you can kind of take the input, squish it down, and get a hash value. If it matches the hash that you're told it should hash to, you know it hasn't been altered. Cool. If you take that hash and encrypt it using a private key, then anybody with that public key can decrypt the hash and compare it to the hash of the actual data. And this does two things. Number one, you know the data has not been changed because the hash values match. But number two, you know that the owner of this private key had and referenced the exact same input document, because that signature, the encrypted hash is called a signature in this case, that signature could only be produced by this exact input document and that private key, because it matched the public key that you used to decrypt it and then do the comparison. This signature is what underpins all of the certificates globally. I can take my own certificate and say, here's the public key, and I'm going to sign it. That doesn't really mean a whole lot, does it? Any Joe sysadmin out there anywhere could create his own certificate claiming that, hi, I am Office365.com, and sign it. Does that mean we should trust it? No, it really doesn't. So it's more useful if I produce a certificate, I will take that public key, my public key, and send it to a certificate authority and say, I would like you to sign this. The certificate authority looks at it, verifies everything is good according to whatever method they're using. We'll get into that next week. But then they take the hash of my public key and they use their private key to encrypt the hash so that they are signing it. They are saying, yes, this public key for the Nextdoor NetAdmin has not been changed, and we, the certificate authority, are certifying to everybody else in the public that we have seen it, it has not changed, and we have verified it, and we have marked this by signing it with our private key. Anybody out there with the public key for the certificate authority can look at it and say, this certificate authority signed it. And then they can compare the hash value and say, and this certificate is good, it has not changed. We now know that we have a valid public key for the Nextdoor NetAdmin, and we can use that public key to encrypt any communication going to that server, and we know that it's good. How are certificate authorities chosen? How do you do this? Well, there are ways to create your own certificate authority and to manually instruct all of your devices to trust that. This is something that is perhaps a little more advanced, and we're not going to get too deep into it. But there are a number of public certificate authorities, and they have a lot of requirements for their physical security, for their electronic security, and everything else to safeguard this. But when a public certificate authority goes through all of these steps to verify that everything is good, then another authority, usually the browser or the operating system, Microsoft has a root certificate program. Mozilla for Firefox has its own root certificate program. Google has a root certificate program for Chrome and Chrome OS. Apple has its own root certificate program for everything Mac, iPhone, iPad, all of that. All of these gatekeepers, vendors, manufacturers, whatever word you want to use for them, they will assess the security practices of the root certificate authority, and if it's all good, then that root certificate will be added to the operating system or to the browser as a valid, trusted root certificate authority. And then anything that that certificate authority signs can be trusted. And again, I am generalizing somewhat here. In an actual PKI infrastructure, you will have multiple levels of certificate authorities because you don't actually want your root certificate authority to sign every person's certificate. There's security reasons behind that, but I'm not going to go into that right now. We're keeping things general today. The big important part to know is that there's multiple types of certificates. They work as a public key followed by, well, technically speaking, a certificate itself. Here's what a certificate is. Has a bunch of data, including the domain name of the server, any other domain names it can be referenced by. It'll typically have space for other data, such as the organization, the organizational unit, city, state, country. They're all fields that can be filled out. Not every certificate has them, but it has space for them. Then you'll have the public key of the entity that is claiming the certificate is theirs. And then you'll have one or more signatures by various entities, one of which hopefully is or chains back to a root certificate authority. I will explain a chain because I just used an unfamiliar term. Without getting too deep into why we set it up this way, you can chain things. If I have a certificate and it's signed by you, and you have a certificate that is signed by the root certificate authority, then everything's good. It chains back. The root verified you, you verify me. There it is. Cool. So that's what I mean when I say chains. It needs to chain back there eventually. Certificates are an immensely complicated subject. So don't feel like how do I phrase this? Certificates are just an immensely complicated subject, and I could go on for hours and hours and hours, but I'm not going to go on for hours and hours and hours. Don't feel bad if you don't get it right away. Sometimes it'll just take time. Or just enjoy this video for what it was. In either case, what? I don't know. I was saying something. Hi. In any case, thank you very much for joining me today. I am your next door netadmin. We'll see you next week.